So in this section, we're going to take what we've learned about partial derivatives and use this to look at tangent plane approximations and differentials. So we're going to start with some refreshers from Calculus 1. So recall if we have a function y equals f of x here, and we look at the point x equals a, we can take the tangent line at that point, which we're writing as y equals L of x. So if you recall from Calc 1, this is given by y equals f of a plus f prime of a x minus a. And so we set L of x to be this tangent line. So L of x is f of a plus f prime of a x minus a. So we view this as a new function now. In Calc 1, we referred to this y equals L of x function as the linearization of y equals f of x at the point a f of a. Because basically it's taking our function y equals f of x, which is in general not a line, and it's pretending it's like a line, or it's pretending it is a line near the point x equals, or near the point a f of a. So we're linearizing it. We're pretending it is actually a line when it's not. So now we want to consider what's this going to look like in multiple variables here. So recall we saw before when we were looking at functions of multiple variables that a plane in three-dimensional space is given by an equation like this, where c1, c2, and c3 are constants. Now, if there's a particular point we're interested in, like the point AB in the xy plane, we can shift this equation, much like how we had the tangent line we had an x minus a term in that. We can do the same thing and write our tangent our plane here is d1 plus d2 times x minus a plus d3y minus b. So this is writing it where it's the plane equation now where it's focused on the point AB. So in particular, we can relate these things. So if we were to take d1 to be c1 plus c2a plus c3b, d2 to be c2, and d3 to be c3, then these two planes given here are actually the same plane. They're just different representations for us. So we've taken that first plane and really made it focus on the point AB. So now we're going to use this to look at tangent planes. So recall we saw before, given a surface z is equal to f of xy and some point AB, we had a bunch of different tangent lines through that point to the surface, and putting all of those tangent lines together gave us a tangent plane. And so we're writing this tangent plane as z is equal to L of xy here. So this plane just touches here at this point. So this point here would be AB, f of AB. And so the plane's just barely touching the surface there. So obviously what we're looking for here is much how we had an equation for the tangent line, and we use that in Calc 1. Here we'd like to have an equation for the tangent plane. So let's go ahead and let this L of xy, we know it's a plane, and we're focused on the point AB, so let's write it in this form that we saw, where we have d1 and d2 and d3 are constants, and we're writing it in the equation form for a plane where we're focused on the point AB. And so what we'd like to do is we'd like to calculate these constants. So I want to know what d1, d2, and d3 are. Now, if I look at this equation for L of xy, and I plug in x is equal to a and y is equal to b, the term with d2 and the term with d3 are both going to be 0, so we're just left over with d1. But we also know that L of AB is f of AB because it's tangent at that point. So if we go back here, L of AB is at this point, which is the same as f of AB. So we know L of AB is f of AB. So that tells us that d1 has to be f of AB. So we figured out one of the constants. That was really easy, actually. Now the other two are a little bit more complicated, and we're going to make use of what we did last section on partial derivatives. So we have our surface graphed here again, and let's go ahead and fix a value of x just to be a. And so remember, we had this exact same picture when we were looking at partial derivatives, and we see this orange curve here is the curve z is equal to f of a comma y. So y is allowed to change there, but x is fixed to be a. So this should look familiar from the last section on partial derivatives. Now let's go ahead and throw the tangent plane onto our picture here. So here's the tangent plane now. So notice we still have that orange curve where x is fixed to be a. And now let's go ahead and what does L of AY look like? So that should just be a curve on the plane. So we add that on now, and so that's in a purple here. So notice everything here is in 3 dimensions, but if we focus just on that orange curve and that purple line is exactly the tangent line to that orange curve. And this should look very familiar from the section on partial derivatives now. So if I plug in x is equal to a, the term d2x minus a goes away, and we've already figured out d1 is f of ab. So I'm just left with L of ay is f of ab plus d3 y minus b. And we just saw on the previous slide that curve z is equal to L of ay is exactly the tangent line to the curve z is equal to f of ay. So that was the purple line tangent to the orange line. But this should look super familiar because this is exactly how we define the partial derivative. Namely, the slope of this line is how we define the partial derivative with respect to f, or of f with respect to y at that point. So that means this equation here, the slope of this line here should be the partial derivative. So that tells me d3 has to be this partial derivative of f with respect to y at ab. And so we can go through the same argument now where we fix y to be equal to b and let x vary, and that'll give us d2 is equal to f of x, f sub x of ab. So it'd be a good idea to pause the video right here and go ahead and work through that on your own to make sure that you understand where that's coming from. So once you do that, you can continue on. And so we found all of the constants now. So that tells us our tangent plane here is just given by L of xy is f of ab plus the partial derivative of f with respect to x of ab times x minus a plus the partial derivative of f with respect to y of ab, y minus b. So it's important to note here, since we're plugging in ab to the functions, f of ab is a constant, f sub x of ab is a constant, and f sub y of ab is a constant. So this really is a plane. And you can compare this to the formula for the tangent line and look at, we still have what's matching up here is you have the value of the function, and then you have the slope, the slope of the function. So in this case, we have a slope in the x direction, a slope in the y direction, and then times a minus b and y minus b. So you can see it has the same flavor as the tangent line equation did. So one of the reasons we learned tangent lines and we cared about those is we could use them to approximate function values. So let's go ahead and refresh our memory on that. So we could use this to approximate the value. So notice here, if I have my tangent line, if I'm interested in the value of the function f of ab, say, for f of x0 here, I want to know what this value is, and I don't know how to evaluate my function at that point. Well, the tangent line is just a line, so I know how to plug a value in for that. So even though these dots are not exactly equal, it's a pretty good approximation to say L of xy is about the same as f, or L of x0, is about the same as f of x0. And the closer x0 is to a, we see the better that approximation is going to be. And that was one of the reasons we studied tangent lines in Calc 1, is to be able to do these approximations. Which should give you an idea of where we're going with this. We're going to want to do the same thing with tangent planes. So suppose now we have some value f of x0 comma y0, and we're interested in the value of the function at that point, but we don't know how to evaluate the function. So what we can do is hopefully we can find a point AB that's close to x0, y0, and that we know how to evaluate f of AB. And then just like before, we can say, well, I know how to evaluate this. I can evaluate this because this is just a plane, so it's just plugging in some numbers and subtracting. And as long as x0, y0 is close to AB, hopefully this f of x0, y0 will be close to L of x0, y0. So it's the same idea as we used for tangent line approximations. We just have one more variable now, and we're just using the tangent plane. So we'll see, we're not doing any examples of approximations with tangent planes in this video, but in class we'll see lots of applications of that with some real world examples. This is just to kind of get us up to speed before class for that. Normally when we studied tangent line approximations, we also studied differentials in Calc 1. So let's review our differentials in one variable. So we have our function here in one variable, y is equal to f of x. So let's recall what our differentials were. So we're going to fix some x values, a and x0, and we're going to let dx, which is also denoted delta x, to be the difference between these two values. And we're going to set delta f to be f of x0 minus f of a. And now df, so f of x, delta f is generally what we'd like to compute, but in general we know f of a but we don't know f of x0. Now df is going to be L of x0 minus f of a, and in general we know how to compute L of x0 and f of a, so df is something we can compute. And if we go ahead and plug in the formula for L of x0, we see that f of a's are going to cancel out, and we'll be left with f prime of a x0 minus a. So you can go ahead and pause the video and work that out if you don't remember it from Calc 1. And so that x0 minus a, notice, is delta x. So our delta f was approximately df, which is f prime of a delta x. So we could approximate this delta f by calculating df. So let's go ahead and look at a picture of what was going on with this. So notice here the dx, the delta x, is just this distance here. And now delta f is the exact change between f of x0 and f of a. So that's this height here is our delta f. And now df is the difference between L of x0 and f of a. So df is this height. So what we're saying is, as long as x0 is somewhat close to a, the height here is about the same as the height here. So that's all that this is saying. And now just like we reviewed our tangent line approximation and then generalize that to get a tangent plane approximation, we're going to do the same thing here, and we're going to consider differentials with two variables. And of course, we can do tangent planes and differentials with more variables. We just lose the ability to draw pictures to understand things geometrically. So now we're going to fix a point AB. And in general, like we've seen before, we want to be able to evaluate f of AB in order to have this be useful. And we're going to have some point x0, y0, and we're going to be interested in the value f of x0, y0. Or maybe we're just interested in the difference between f of x0, y0 and f of AB. So now we have two independent variables, x and y. So we're going to have a dx, which is going to be delta x, which is x0 minus a, and similarly for dy. And we're going to take our delta f to be the difference between the value we're interested in and the value we know. And we're going to let df be the difference between the tangent plane evaluated at the point we're interested in and f of AB. And now we recall that we just saw a couple minutes ago that we have this equation for our tangent plane. So we can go ahead and see that the df then, if we plug in x0, y0 into L of xy, and then subtract f of AB, well, that will get rid of the f of AB here, and it'll just leave us with this stuff left over, except we've replaced x with x0 and y with y0. And remember, that is the delta x and the delta y. So we just have this left over for the differential. And this looks very familiar. This looks very similar to what we had in the one variable case, where we have the derivative of the function at a point and then the delta x. It's just since we have more variables, we have two partial derivatives here to deal with. And we'll say, just like before, that delta f is approximately df, and the df is something we should be able to calculate. So let's go ahead and end with a picture of what this is doing here. So just like before, the delta f is the exact change in the function. So this is the height we know. This is the height we're interested in. So the difference between those two heights is my delta f. And then I go over here and I have L of x0, y0. And the difference between that and f of ab is our df. And now the picture looks like it's a huge difference between delta f and df, but this is just drawn this way. I drew this a little bit exaggerated so we'd be able to see everything in the picture a little bit easier. But as long as x0, y0 is close to AB, the difference between this height and this height will be quite small. So just like with the tangent plane approximations, we'll see examples of this in class as well.